So now we are going to be talking about the second kind of undersampling techniques, which is called the cluster centroid. The cluster centroid technique basically talks about the fact that instead of, so you have your imbalanced data which looks like this, right? So this is a negative class, right? So this is, instead of basically randomly sampling from them, what this says is that take this negative sample and cluster into multiple points, and out of those multiple points basically take the cluster centered, which is basically a representative sample from the cluster. So the idea is take the negative class and break it into multiple plots, and then instead of taking randomly points from there, take basically the points which are basically the center of each of these clusters. So that's the concept that is cluster centroids. So cluster centroids in this example, let's understand this with a concrete example. So if you have a minority class which has got 200 examples and majority class which has got 1000 examples, what you're going to do is basically take those 1000 example of the majority class and cluster them into 200 clusters. And once you get those 200 clusters, then basically take the cluster mean of each of those clusters. Now obviously you don't understand at this point how clustering exactly works. So there are some concepts which are still dodgy, but understand the whole idea is that instead of randomly taking 200 points from that 1000 points, just break them into 200 very similar, so that the whole idea is you want unique data points, right? You don't, if you're randomly sampling, you could probably end up with data points which look very similar to each other. So instead of doing that, the better idea is basically first take those 1000 and break them into unique clusters, right? Clusters that are very similar within themselves and very different from each other. And once you do that, then take the clusters and mean or anything which is basically a representative sample from that cluster. And that's the whole concept of undersampling, so that we stack the minority class with as many unique examples as possible, right? That's the whole concept behind cluster centroids. So you're going to take the majority class and I'm going to split it into multiple parts, multiple unique parts, and from each of those unique parts I'm going to take a sample, representative sample, which is mean in this case, right? So that is the concept of cluster centroid. So now let's again do the same thing. So you can see here, once you do the undersampling, we are again left with 140 examples. Just keep in mind before we kind of do the rest of it, in this case we are basically not taking, so earlier case we were basically taking some of the negative examples as it is from the negative or majority class examples as it is, right? In this case you are not going to take the majority example cases. You're basically, there's a very high chance that you would be basically be taking a mean of those negative sample classes, right? Please understand this, that you are changing the data. In earlier case, you are not really changing the data, you are basically just dropping off some rows. In this case, you would be basically not only be dropping off some rows, because you would be taking mean of each cluster, you would basically be changing taking a very different data set, right? So just keep that in mind. This is something slightly different from what you do in random undersampling, right? Undersampling, you just was basically dropping off certain rows randomly. In this case, it's not the thing. You're gonna be basically taking some rows and then taking a mean of those rows, and then that is a new row in the data set. Obviously it's gonna be lower number of rows, but it's not gonna be the exactly same rows as what you had in the original data set. So that's about cluster centroids. So now you do the same thing that we did earlier. So now you see random forest has improved to 0.73 AUC, right? And what about our logistic regression? 0.76, right? So this was random. So now we check for cluster centroid, so CC. So CC we have 0.73 and we have 0.76 here. So this is again back because obviously, as you can clearly see here, this is better than this, which is probably because you are using a more sophisticated technique here, but this is still lower than this, right? So this is a base level. So this jump is still, there's still a stark difference, there's still at least a considerable significant difference here also, right? So this difference is also because of the fact that undersampling is happening here. You are basically giving it a lot less data to learn from, and that's why it's not able to fit in here. So that's the understanding to take away from here, that this model is still not as good as this, because this is learning from more data points, this is still learning from less data points, right? So all of these points are gonna have 280 data points, right? Whereas this adds around 600 data points. So as you can clearly see, logistic regression is not something that is affected as much by the size as is random forest, because random forest, if it gets a smaller data set, it would tend to overfit, right? So that's why this significant drop in performance. So now let's try and go and understand the third and the final undersampling concept, which is called Tomek Links. So Tomek Links is basically nothing but you basically getting rid of some majority class examples. But how you do that is basically the question, right? Anyways, the concept of undersampling is you need to get rid of majority examples. In case of random undersampling, it was randomly dropped. In case of cluster centroid, you took them into unique clusters, and from unique clusters, basically you first broke them into unique clusters, and from each cluster you took one. And in Tomek Link, the concept is that each majority class, you basically, for each minority class, you see basically which are a very similar majority class and remove them from the data set, right? So Tomek Link is basically considering the fact that this is your entire data looks like. So now your circles are your majority class and your crosses are your minority class. So as you can see, what I'm doing is for every cross here, so we are basically finding out which is the very similar nearest circle to it, and basically what the next step would basically be removing all of these circles, right? So in this blue box, in this blue circles, you are seeing the pair of negative and positive examples. So your crosses are your negative, or basically the majority class, minority class. So these are the positive examples, and your circles are the negative or the majority class. And what you're doing here is basically for every positive or the minority class, you're basically checking out which are the very most closest negative class instance, majority class instance, which is nearest to that, right? So for every minority, which is a majority instance which is very similar to it, and then just removing those majority simple. So the idea is that basically by doing that, what you can clearly see here is you have made the decision boundary, kind of the separation between the positive and negative examples very clear, right? So you're basically removing examples from the boundary, and because of doing that, you have made the decision boundary of sorts, right? Manually you have done it, you have made it very clear, right? Because you have basically removed everything that was slightly confusing, right? It would be very tough to fit a decision boundary out through this all examples, right? But to fit through something like this would be roughly very easy, right? So this is the whole concept of Tomek Links. For every minority instance, you basically see what is a very similar which is a very similar majority instance, and just get rid of that, right? So that way there are two things. One, obviously you got rid of some majority instances. Please keep in mind, you're not removing the minority instance, right? The minority instance still stays. All you're doing is just remove this majority instance, right? So that kind of helps you in kind of undersampling this majority instance. And also the second added advantage of this kind of advanced technique is basically the fact that you are ending up with a much cleaner decision boundary here, right? The separation between positive and negatives are very good. So that's exactly something. Again, now we are going to take up the imbalanced learn data library and kind of try using Tomek Links and see how it goes. So first we fit a random forest, and in random forest we see the AUC has dropped down again to 0.729, which is roughly 0.73. Which is roughly 0.73, and our random forest is even better, right? It's at 0.77. So let me write that. So this is Tomek Links. Tomek Links is the performance almost 0.73. Here it has gone up to 0.77. So all of these are on roughly 280 points. So as you can clearly see here, the performance here has stayed almost similar because there's not much of a difference out here. And I've already explained to you, both of this are really good. As compared to say this was the worst one, because we can clearly see random undersampling was not the best. We used some more sophisticated techniques out here, and using sophisticated technique kind of improved our performance, but obviously it's still not as good as the original performance, right? Because this was on 600 data points. All of these are on lower data points, right? 280 data points. So smaller data random forest tends to overfit. With this kind of Tomek Link kind of a thing, the only thing to remember is that you would tend to expect that your model performance should go up because you have kind of cleared out the data set, but that is for a training data set, right? Please remember, this is what you're doing for training data set, right? So for training, you're basically making it easier. which also basically raises the concern that what happens now if you're in your test data set, your problems, your data points actually lie along this line, right? So then your model obviously would be having a tough time. So depending on that, Tomek Link could be a good example, good way of undersampling or not, is basically on the fact understanding if your test, because in test time you really don't know which is what, right? If it's a positive or a negative instances. And now if it happen to be that your test examples are all around this line, right? So they're all around the decision threshold. So just because basically you did clear them off, that means the model did not learn anything around this kind of decision boundary points, right? So that's the understanding. So we have seen that in case of undersampling as such, our model was not performing as good as, at least random forest is definitely not performing as good, right? So given that is the concept that we have in mind, so let's try and see what oversampling has for us.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.